Hello everyone, I am Rajesh Punya and I welcome you all on my YouTube channel Punya Chem Classes, and today we will discuss about the entropy, which is an important topic in the thermodynamics, and mainly 2-3 question comes from these topics in the CSIR net exams, and similarly 1 or 2 question from the uh, in the from this topic in the gate exam also. So this is an important topic from exam point of view, and we will study today this topic in very detail, and we will start from basics, and then we will learn different formulas of entropy and how to use that formula in different cases according to our problems. Uh, let's start the topic. Entropy is the measure of randomness or disorderness in any system. More the randomness in any systems, more will be the entropy. First, the entropy is defined from the statics thermodynamics. According to statical thermodynamics, the entropy S is equals to K ln W, where K is the Boltzmann constant and W is the thermodynamic probability. For the completely ordered system, the value of W is equals to 1, and there is no entropy in that system. Means for a completely ordered system the value of entropy will be 0, and if there is some disorderness in any system, then the value of W is not equal to 1, and there will be some entropy in that system. Entropy can be also defined as quantity of heat absorbed is isothermally and reversibly divided by the absolute temperature. These equations can be derived by using the second law of thermodynamics. Now we will discuss about some properties of entropy. Entropy is a state function because it depends on the initial and final points only. It's not depend on the path, and it is an extensive property because it's depend on the quantity of the substance involved in any chemical reactions. Means how many number of moles we are taking of any substance that, and these are the units for the entropy: calories per degree per mole and joule per degree per moles. And now we will discuss that how entropy is going to change, that whether entropy will increase or decrease in different chemical reactions. So as I already told that entropy is a measure of randomness or disorderness. So in the case of gases, there will be more randomness, so entropy will be the highest in the case of gas, and then in the case of the liquid, and then entropy will be the least in the case of the solid, because the randomness or disorderness in the case of solid is very less. So in solids have a very less entropy. So that if the number of moles, change in the number of moles for any chemical reactions is positive, then entropy will increase, and if the number of moles, change in number of moles is negative, then our entropy will decrease for that chemical reactions. So that and if the atomicity is increases, then entropy will also increase. See here in NO2, if we have to compare the entropy for these two substance NO2 and NO, here atomicity is 3 and here atomicity is 2. So the NO2 have high entropy as compared to NO. So we can compare in this example also. Here the number of moles is 1, and now we for this chemical reaction, the change in the number of moles is positive, so the overall entropy of the system will increase for this reaction. So in the next case we will see that how to compare the entropy for the same atomicity molecule, and if the number of moles is also same. See, if atomicity increases, then our entropy will also increases. If change in number of moles is positive for any chemical reaction, then our entropy will increase. So what will happen if both these are same? So this is the next case. If for a same atomicity and same number of molecule, the entropy change in entropy will depend on the molecular weight. Higher the molecular weight for a molecule, more will be the entropy. See, for O2 molecule and N2 molecule, O2 molecule have high molecular weight, then so it has high entropy. So change in entropy will be highest for oxygen as compared to nitrogen. And next we will learn that how entropy is going to change in different processes, that when how entropy is going to change in reversible process and in irreversible process, and the effect of changing different parameters like pressure, temperature and volume of an ideal gas, and how entropy is going to change when we are changing our phase, and entropy change on mixing of ideal gases. We will learn all these things. And first we will learn that how entropy is going to change for a ideal gas, by changing different parameter like pressure, volume and temperatures. For that we have two expressions which is really important from the exam point of view, and we can solve many questions by using these two formulas only. The first expressions tell us that the change in entropy when we are changing our temperature from T1 to T2, and when we are changing our volume from V1 to V2. And this expression is delta S is equal to Cv, which is a specific heat at constant volume, ln T2 by T1 plus R ln V2 by V1. This formula is used when we are changing temperature and volume. Then we have to use this formula. And if we are changing temperature and pressure in our system, then we have to use this formula. uh, the formula is the change in entropy is equals to specific heat at constant pressure ln T2 by T1 plus R ln P1 by P2. This is for change in temperature and pressures. The derivation for these formulas are not much important, but still for the sake of knowledge we can try the derivation for this for this one formula, and for other similarly you can do that. Yeah, let's try the derivation. And this is from the definition of the entropy, that delta S is equals to heat absorbed by absolute temperature. And from the first law of thermodynamics we know that delta Q is equals to delta U minus delta W, and the value for the work, uh, for the expansion of work, this is uh, expansion of work, expansion of work. This is not for compression, this is for expansion. Then value of W is equals to minus of P dV. When we will put this value of W in the above equation, then we will get that delta S is equals to delta U plus P delta V divided by absolute temperatures, and by cross multiplying we will get this equation. Now we can put the value of internal energy in terms of specific heat at constant volume. We know that specific heat at constant volume is equals to rate of change of internal energy divided by change in temperature, uh, rate divided by change in temperature. When we will put the value of internal energy in this equation, we will get this equation. So now as we are changing our temperatures from T1 to T2, and our volume from V1 to V2, we on integration finally we will get these equations. Now this derivation is not much important from exam point of view, but we have to remember this formula, because we can make some further modification in this formula also. See, this is the formula for the change in entropy when we are changing our temperature and volume. We can make some modification in this formula also. Suppose our process, we are making our process isothermal, means we are keeping our temperature constant. Then the value of the initial temperature and the final temperature will be equal, and this whole term will be become 0, because this term will be cancelled and the value for ln1 will be 0. So the our formula will becomes uh, change in entropy for a isothermal process will be equal to r ln v2 by v1. Similarly, if we are making our process isochoric, means we are keeping our volume constant. It means initial value of volume is equals to the final value of volume. Then this term will be cancelled out, and we are getting the formula delta S is equals to cv ln t2 by t1. Similarly, we can make further modification for the change in entropy during when we are changing the value of pressure and temperatures. Means first we can kept constant temperature constant, means for isothermal the value of delta S will be equal to r ln p1 by p2, and for isobaric process the pressure will be the constant, and the value of delta S will become cp ln t2 by t1. And now we will see the change in entropy when we are changing the phase of the system. See, two type of phase transformation can be takes place. Either it can be reversible phase transformation, and it can be irreversible phase transformation. In both case, we will study that how entropy is going to change during these two processes. First, we will see that how our entropy is going to change when reversible phase transformation takes place. In reversible phase transformation, the change in entropy is the ratio of the heat of transformation and the temperature at which the transformation is taking place. So let's take one example. Suppose our system is going to change its phase from liquid to vapor. So this process is called vaporization, means going from liquid to vapor is called vaporization, and this process will take place at the boiling point of that system. So the change in entropy will be defined as the heat of vaporization divided by its boiling point. So change in entropy will be taken as entropy of the vapor minus entropy of liquid, means final state minus initial state. So this is the overall change in the entropy in that reversible phase transformation. Similarly, you can try for condensation, freezing, sublimation, and deposition, and see that whether the deltas will be positive or negative. Okay, now we will see that how entropy is going to change in irreversible phase transformation. See, and now to find the entropy change in irreversible phase transformation, uh, first of all we have to convert all the irreversible phase into a number of reversible phase transformation. Okay, so let's directly take one example and then only things will be more clear in these type of problems. So it is little bit confusing. Yeah, this is a particular problem in which water is going to change its phase from liquid to vapor, and here temperature is also is going to change from 25 degrees Celsius to uh, 125 degrees Celsius, and pressure is remain constant during the whole process. So this problem has total uh, three reversible phase, and then we to get the total change we have to add all those three uh, reversible process. So first step that we have to do is in this type of problem that, we have to change the temperature of the system where up to where that phase reversible phase transformation can take place. See, for water the boiling point is 100 degrees Celsius, so only at 100 degrees Celsius the reversible phase transformation can take place. So we have to increase the temperature of this water from 25 degrees Celsius to its 100 degrees Celsius. So for that, the change in entropy, we can easily find out that here the pressure is kept constant, so this is an isobaric process. And I already told these two formula. We can get this formula from the I told that the two formula by keeping the pressure as constant. So we will get this formula. The change in entropy is equal to Cp ln 2. Now we increase the temperature up to its boiling point. Now here reversible phase transformation can be takes place, and for the reversible phase transformation, and the change in entropy is equals to heat ratio of the heat of vaporization to its boiling point. See, here the phase transformation is going from liquid to vapor, and that's why we are using heat of vaporization. And then finally we can increase the temperature of the system from 100 degrees Celsius to 125 degrees Celsius, and for that the change in entropy is delta S3 is equals to specific heat at constant pressure, and ln T2 by T1. Here T2, the value for the T2 is 125 degrees Celsius, and value for T1 is 100 degrees Celsius. Net Now to get the net change in entropy we have to add all these three equations. So in irreversible phase transformation you can get these type of problems. And the entropy can also be changed by mixing of different ideal gases, and this topic we will learn in our next class. And in next class we will do some problem based on these two topics also. And thanks for watching, and if you like this lecture then please share this video and subscribe my channel. Thank you.